All right, hello everyone. Welcome back. Happy Monday. Hopefully nobody has a case of Monday. All right, couple of housekeepings. We are reminding you that you should change your name and last name on Discord to your first name and last name. If not, you can leave. You have to know who's there. So there's no anonymous sending messages, right? We need to know who we're talking to. September 28th will be no class. I think it's a Wednesday. I won't be on campus. I will send an announcement. I think we can put like a announcement and tag on Discord, something like that. I'll put it on Carmen as well. I posted 2 examples for PA assignment 1. These are just example ideas. How would you write? So 1 quick explanation. Well, 2. First, if you're here, you really like robotics and you wanted to know what is it all about, right? So it's an elective. So you are expected to go the extra mile. It's not a bare minimum kind of course to get an A and B. Bare minimum probably gets you C. All right. 2, if you are going to work in the world of robotics, your customers usually might not know everything about robotics. So you really need to understand and use the need of your customers or user. So anytime you code something, you have to remember, they don't know all the equations stuff we know. Use the prompt. When you run a code, when you run a software, you always get a prompt. What is the software about? What is the problem that's being solved, right? It's just fprint 3 sentences or fprint 1 sentence. What is happening here? All right. Use that. So the grader, I haven't checked the way grading happened, but I think the average is about 80 something, which I'm happy with. And I asked him to give you enough comment that you'll be able to write the next one better. So if you did bare minimum, you did not get the whole point, even though you had the final answer correctly. That's not the idea and point about this class. If that's the thing, you need to come talk to me. All right. So I will convince you that that's the wrong way to go with. All right. So, but if you have any issues with grading, email me or stop by office hour. We can talk about it. 1 person submitted the homework. I think they just submitted a wrong file. So I'm sent a message. Don't submit wrong files, right? Because then Carmen would not show you that you have something to submit. You get a 0. All right. For this week, for today, there will be no class participation because I want to finish homogeneous transformation, and then you're gonna have a class participation on Wednesday. So I want you to listen and come prepared for Wednesday. All right, then we'll solve 1 class participation in the classroom. The fishbowl, there was a comment that there isn't enough time for class participation. So the ones that are longer, I usually give you more time, like Fridays that you have time until Monday. If something, I give you only 5 minutes, I usually give you point based on completion, right? I just want to know if you got the point quickly. Even the last class participation number 4, even though you had time over weekend, I didn't deduct too many points for the wrong answer and not showing your work. When I say show your work, show your work. If you don't, for example, in your homework or in your exam, you will lose half of the grade, because if I don't know what happens in the process, the correct final answer really doesn't matter to me. Because if I change the problem, can you still get the right answer? I don't know if you don't show me the process. All right. So these are all warnings, one-time warnings. So next time, if it happens, you'll lose more points. And losing points is just to grab your attention. So if you lost 1 point, I wanted to grab your attention and to check a comment that I left. Sounds good? All right. So for today, I'm going to go over what was left from last class after my computer shut off. And then Zoom. We will start the new topic. All right. I think you were here. Any question on the roll pitch yaw part of the? So we had 3 different type of representation with 3 parameters, right? So one was, what was the first one? Euler angles, right? So you had the first rotation and last rotation similar. The one in the middle was different. You have 6 different cases. So there are 6 ways that you can represent the rotation using Euler angle. Then we had rho pitch yaw, also 6 different combination. But for rho pitch yaw, you remember when we said that those will be very beneficial to use those angles representation? Remember airplane, and then they have control tower. So application that you need some observer on the ground to be able to understand the rotation matrix. So it's easy to convert between them, right? So if you're dealing with hexacopters or anything that flies, probably that's what you are going to use. If you're dealing with industrial robots, probably Euler angle. Not necessarily, but sometimes makes your life easier. All of this, and the third one was axis angle rotation, more generalized. All 3 of these are applicable to all problems. Sometimes some are easier. You will learn those based off experience. So you can't give me a problem. It's like, what do you think is the best way to go with? I don't know. I've never seen this problem before. I'm going to learn. All right. So that will be your case as well. But you need to learn all 3 of them. For rho pitch yaw, I think the one thing I didn't mention is that let's say you have X, Y, Z rotation around X axis, Y axis, Z axis rotation. So the first rotation is called the parent. All right. Then the second is the middle. And then the last one is the last child. So the middle axis is important because you can have gimbal lock happen when your parent and your middle axis are aligned. So you're basically losing 1 degree of freedom, right? So if you don't know gimbal lock, I posted a video in that page for the lecture. Go watch that to understand what is happening there. The video is really self-explanatory, and using rho pitch yaw, you have to be careful about the gimbal lock. All right. This one was the third one. We said that what if we wanted to introduce a vector as our rotation axis, right? Vector K, and then to understand the rotation theta. Now, we solved an example, kind of went through an example. I'm going to do that again here. But the idea is that, let's say this is axis. So this is our frame X0, Y0, Z0. We are rotating it to this frame 1, Z1, X1, here, Y1. All right. So we want to know the rotation that happened in frame 0. What's the representation in frame 1? So what happened here was that the first frame rotated alpha about the z-axis of the original frame, and then it rotated beta about the current frame y-axis. So this going from R0 to 1, there are 2 rotations about the z and alpha, and post multiply by r, y, and beta. Now, from the similarity matrix, the similarity theory that we just learned last class, and you had to submit a quiz or a file about that, the similarity matrix says that if we have a representation, a rotation in one axis, and we want to know what is that rotation from a different perspective, we could use the inverse and the rotation between the 2 and find the new axis. So basically, we are doing that. So R, K, and theta are new rotation in frame 1, right? Frame 0 rotated to a new frame would be R01 inverse, R, Z, and theta. So theta rotation about the Z axis of the original frame. We want to know what would it be about K, which is in the new frame. And 0 and 1 are between frame 0 and frame 1. Now, if we replace R01 here and R inverse, so RK and theta becomes RZ and negative alpha from here, R, Y and negative beta, RZ and theta, RZ and alpha, RY and beta. Where did I get these all from? They're from top here, right? So these are my R1, so I got the inverse of that. And then just need to sandwich RZ and theta between that. Now, since all of these are about the principal axes, we actually have all the rotations. So if you put all of these together, multiply them all, do some math, you get to this last matrix. So we're going to just use this because you're engineers, right? You like someone else's hard work. So we are going to use this as rotation matrix about axis K, which is a vector we define, and a theta degree. Those are 6 elements, right? So this is basically your R11. This is your R12 and go on. And the shorthand for V theta is 1 minus cosine of T. Now, if I give you a rotation matrix and I say, can you represent this as if this rotation happened about a vector K and a theta angle? You will be able to find those K and theta using these two relationships, right? So theta would be the trace of that R, which is the diagonal element, and then K would be following this relationship. So Kx, Ky, Kz. So you have the vector and you have the theta. So these are all repetition of what we talked about on Friday, and then this is just for the sake of recording for future. Now we also solved, so find theta here, then find K here. So K is a vector. Now we solved this example, right? All of you had the correct combination of the rotation. You said this was RZ and theta, which was 90 degree, RY and 60 degree, and RX and 30 degree, right? So these are rotation about different axes with different angles. Then what was the next step? Do you remember this example from Friday? Or you want me to explain it? Oh, 30 and 60, okay. Is that the confusion? Are they all pre-multiplication? Right, yeah, okay. Good catch. All right, so but RZ and 90, followed by this for all about fixed axes. So RY 30, RX 60. There you go. All right, what we wanted to find here? What did we want to do with this example? Do you remember from Friday? Max. There's only one max. Do you remember this example from Friday? No. Okay, who remembers? All right, Nathan.
Another matrix that's equivalent to also rotation.
So this is rho Picciol, right? A combination of rho Picciol rotation. We said that you should be able to move transition between one type of representation to another type. That's what we're trying to do here. This is a rotation matrix resulting from a rho Picciol. Now, can we represent this? Can we calculate an angle that if you just rotate it about that axis, it will give you the same rotation? Yes, we can, right? So if do we have all of these 3 rotations? The matrix, the values. We do. These are all basic rotations, right? So just go find the basic rotation, we plug them in, and let's say I'm gonna write down. So this, what I'm writing right now is backward because I didn't pay attention about fixed frame, but I'll fix that. You know what? No, I'm gonna do something I'm gonna cheat because I can, because I teach this class. Problem solved because I have the answer backward. If you are that smart on the spot, yes. Yes, if you are not nervous and do that, I accept it. And this is on the record. All right, so R is cosine of 90. I'm just going to use shorthand. Negative sine of 90, 0, sine of 90, cosine of 90, 0, 0, 0, 1. That's for Z. Cosine of 60, 0, sine of 60, negative sine of 60, cosine of 60. Then the last one, we know about x-axis. Nobody say I'm doing wrong. I can't afford another wrong one right now. If there's something, I'll fix it after I'm done. So the idea is to get here. 0.866, 0.5, 0.5, 43, 75, negative, I'm just gonna do 0.8, 25, 0.43. Okay, so this is my rotation matrix, right? After those three consecutive rotations. Now, how do I find theta? Cosine inverse of the trace of this R that I just wrote, -1 divided by 2. So these three elements are important for trace. You add them together. So it would be cosine inverse of, we've done this already, but again, 0.43 plus 43 -1 divided by 2. This should give us, I think this is the right answer, 84 degrees. So that's our theta. I still need to find the vectors, the vector component. 2 sine of, make sure if you are using your calculator, if this is in degree, you are in degree, not radian. Then 25 minus 75. So what I'm doing here, I'm just following this. Try to find those elements and write them down. 0.5. There's a negative here. 866. There you go. They look better in my annotated version. You can actually read them. Don't worry about it. 6845. So these are kx, ky, kz. So I found a vector and angle. So if I rotated about this vector, let's say my calculations are right, and this angle, it should give you the same rotation matrix. Yes.
I want to know why you use this order, like all of the current, so the order of 90 is
This is 30, this is 60. All right. But do you understand the rest of it? Yes? So, again, I love students. They pinpoint that one negative or one number you're wrong, but they miss the whole point. The whole point is being able to use the equations, right? But good catch, but this and these are really, really important, all right? Now, if I ask you, okay, right, can you represent these in Euler angle? What is your answer? Yes, very, very difficult, because then you have to write code for all 6 of those and see which one is this one, right? So usually that's why dealing with path planning is difficult, especially when you see that. It's called inverse kinematic. So you need to put yourself in a position and orientation and try to figure out how did you get there. That's a hard problem to solve, right? So going between going this way is easy from Euler angle to axis angle, or from Rho-Fisher to axis angle. Going backward is harder. You basically have to write the code for all 6 orientations and see which one hands out. All right. So this was the example. I'll fix all the fixes, so you will see the correct ones, which is this version, in my annotated version. All right. Now, you have seen this before, right? Rigid body transformation or configuration. We could have to 3 rotation, about 3 different axes, and 3 translation about X, Y, and Z. Now, when we combine all of these together, we can do that in the spatial Euclidean group S3. So we can have rotation and we can have translation. Rotation is 3 by 3, right? A point, you need X, Y, and Z. If we append these together, put them together, it's like 3 by 4, right? Doesn't look very good. So we introduce homogeneous transformation. We say that you can have a rotation and translation combined together. These first 9 elements are going to represent your rotation. This here will represent your translation. So P1 is along X, P2 is along Y, and P3 is along Z. Now, to be able to do matrix multiplication, for this to make sense, we are going to append these ones that are vectors by 0. This one that's a point coordinate with 1. So meaning that if you have, now if I want to, so this is a transformation when rotation and translation happens at the same time. Now, if I want to represent a point, Q, for example, in one frame that has this transformation, my point is 3 by 1, right? My transformation is 4 by 4 now. What should I do to my point? So I can actually multiply it, because 4 by 4 will be multiplied by what? So this is 4 by 4, right? Do you remember if you had like a 3 by 3 and you said this is P point, so this is PA, you could write PB, right? So 3 by 3 times 3 by 1, it would make sense. But now if I want to multiply this, if I want to transform a point, PA, that is rotated and translated, PA is a 3 by 1. I can't say 4 by 4 times 3 by 1. What should I do?
Make it bigger.
Yes, how? I just said how, but can you
Add 1.
add 1 because it's 1. If I wanted to transfer a vector, a vector is also 3 by 1, right? Add what? 0, because remember, these are vectors, right? Unit vectors, you see, so you don't have to memorize it. That's my point. If you needed to transfer, transfer. If you needed to transfer a point using this transformation matrix, you need to append it by 1. If you needed to transfer a vector, remember my dog and my car? Pepper? If you needed to do that, append that by 0. So homogeneous coordinates for a point P is Px, Py, Pz, and 1. Homogeneous coordinate for a vector, let's say V is Vx, Vy, Vz, and 0. What is funny? Nothing? Okay. So you don't have to memorize these, you just have to memorize this. For this, don't memorize this one, memorize this one. A transformation is a combination of a rotation, 3 by 3. Then whatever is there is 0, right? Because 1 0. And a position or translation appended by 1. This is just to fix our math, basically. All good? Makes sense? All right. And we can apply everything we learned so far to this. Yes.
What is homogeneous in here?
So we are based, well, homogeneous means that, what does homogeneous mean in English? Same. So you could have a rotation and a translation at the same time happening. You can put them, package them in one matrix instead of having a 3 by 3, then 3 by 1. You can package it, but to fix the problem of 3 by 4, we made it 4 by 4. All right. Now, you remember how did we calculate the inverse of a rotation matrix? How? Transpose, right? Pretty quickly, we didn't need to do that. So here, transpose of a homogeneous transformation is not just transpose of it, but it's kind of, because we have rotation, we can use the transpose of the rotation. So to find the inverse of T, your transformation matrix, so T is R, 0, P, and 1, right? To write the inverse, you get the transpose of the rotation, because that should work. Then you get the transpose of the rotation, negative P. You can prove this. It's in your book, if you want to know why is negative R transpose P. Then 0 and 1 stay the same. So this means that T is not equal to T inverse. Right? It's very different. If you have two transformations happening, if you multiply them, it's a still transformation. So transformation matrix 1 times transformation matrix 2 is a still transformation. So remember we did consecutive rotation. We're going to have consecutive transformation as well. Same deal. You can multiply them so they're associated, but they're not commutative. So you cannot say T1 equal T1, T2 equal to T2, T1. Sometimes it is. It's not always. So we assume it's not, and then sometimes you do the calculations. Oh, it's the same. Okay. Depending on what kind of transformation you're actually doing. But you can always say that, hey, I have three transformations. I can multiply the first two times the 1, 4. Multiply the last two, and then you still keep this P multiplied, right? So it kind of should tell you what 3 multiplied post multiply, you can just move them around. So all of these theory will come in handy when you're solving the problem. So, and the good thing is they're all kind of stem back from rotation. So if you understood those very well, these are along the same way with minor changes. Now, do you remember the camera robot coordinate on the corner of the room example? So here we go. Now we have in real life. So we're going to put one reference frame on a camera. We're going to call it, let me call these some numbers so we can actually use. I'm going to call this C, frame C, frame B, and then frame A, the robot. Here's the robot. So there's an R2D2 moving, let's say a robot that is mobile, could be. Or it could be a location that this is reaching to, so it's going to take something from it. Let's put that way. So we're not being mobile robot. This is an arm, and this is the camera on top. So we want to know what's the relationship between these three. All right. Now, we are not just thinking about rotation, we are thinking about transformation. So it could have a translation involved. So all of these are 4x4. Previously, we just talked about 3x3, just the rotation, right? Now, you could say that, let's say, if this was P translation, all right? I could say T of AB is rotation between AB and P in A. So you still have to keep, you need to identify this position in what reference frame. So if I write RAB, which one is my original frame? Based on the script. A. So I'm going to also say where P in A is, right? I'm not changing, hopping between reference frame. All right. If I wanted to know T AC, and this was Q, let's say, what would this be? Just a notation. What did I need to know? RAC and QA, right? Q in A. Now, if you have the information between these two, you have this information. But they're all related, right? So let me add this here. I just said it, but I didn't write it. So this is TAB. This is TBC. This, if you go this way, this is TCA. If you go backward, would be what? TAC. Are TAC and TCA equal? No, it's inverse, right? You have to find the inverse. It might be, you don't know. Where do you find the inverse? This one. So this is one of the equation you want to put in your cheat sheet, for sure. And in the homework and in your exam, please everybody listen, because then some of you say, oh, they didn't know. So in your homework and your exam, if you needed to calculate the inverse of a matrix, you can't just put it in your calculator, give you the inverse. You have to show me that equation. You have to calculate R transpose. You have to show me this is the result of that, and then plug it in. You can check with your calculator that you got it right or not. Does that make sense? So you could have your calculator with you, but you need to show me the process. Any questions so far? Anything on Discord? No? All right, so we want to start walking from frame A around all reference frame. I'm just writing frames and back to A, meaning that I'm going to start here, write all the relationship, go around and come back. So start writing in a new notes. How would you show? For example, the first one, I'm going to write it. Not difficult, just trying to help you with the notation. So this is TAB. Write it for all of them. Okay. Keep talking. Okay.
Go reverse or?
No, walk clockwise all the way back to where you were. We're gonna see something very interesting when we do that. So, write what is hard. So these are consecutive transformation, right? TBC, TCD, TDA. Now, from what we learned before, if I want to write the total transformation that happened, these are consecutive, I can multiply them, right? TAB times TBC times TCD times TDA. All right. Who can see the pattern? Where am I going with it? You're smiling, let me know. Hey, Josh, you know where I'm going with it? So I'm going back to where I was, right? So I did this. Well, my calculus is this. Went to this frame, then went to this frame, and back. You remember, close your eyes, open your eyes, that's the same scenario. So you close your eyes, I went to full frame and I'm back to where I was. You can write the final transformation, multiplying of all four of them. Write it down. So see what happened? I started from a point, went to four different frames, got back to where it was, including the one I am in. You should be able to write your T, final transformation. what is the sorcery? Like, we don't know what those keys are, but.
Wouldn't it be like one in the rotation and then zero everywhere?
Yes, can you explain why?
Because you're just ending back where you started.
So, yes, so let's do this two ways. One, do you remember that very useful subscript cancellation thing? So. Right, so it shows I'm back to where I was. So you can still use the subscript cancellation. Now, since I'm back to where I was, overall, no rotation happened, no translation happened. That's what it means, right? So T, we expect to look like this. That's for rotation. So 1, 1, 1, no rotation, right? Then 0, 0, 1. No translation. So this is your unit transformation. So if no transformation happened, or at the end you got something like that, it just means that you're back to where you started or you didn't move. So we can call this identity. Now, let's say I write another cool thing. Let's start from here. TBC times TCD times TDA. Following the cancellation method, this is what? TBA, right? Now I can write TAB inverse is TBA, right? So you went from one direction, and then you also could go from the other direction. Now this means that if you have, so you have these relationships, right? You can write them as long as you hold this, be careful with these subscription. If you have two of these, so let's say you have these two, you have this one, you want to find TDA, you just write this relationship, you find this. So you don't need to know all of these transformations, you just need to know enough of them to find the one that's missing. And this is a real world scenario, like you know the camera, you know where the car is, you know where the camera is with respect to the corner, so you know where the car is at all times with respect to that corner. Because you have to plug back to your camera. Where the camera thinks the car is, let me check with the corner of the room because that knows where I am. So I know, so the camera knows where I am, something like that. Right? What else here? So write this one in the matrix form. So what's the inverse of that from previous slides? I'm basically walking you through your next past participation, which is the Wednesday. Anyone, what's the first element on that? Yes. R inverse, right? You're trying to find the inverse of that one. Which R inverse of AB and R transpose of AB are the same, so it's interchangeable. Then this one is negative, right? RAB. I always run out of place, so I can put transpose or inverse P. This is 0, this is 1. So here, we know R transpose equal to R inverse. This is all you need to know about transformation. Everything else is built up on top of it. So the mathematics of robotics are simple, like when to use what is a problem. How do I know to use it? Yeah.
Just over.
Over this one more time.
Yeah.
So I just give an example. Let's say if I go from B to A, what one way would be what? And I know that's going from B to A, right? In some amount of motion. Now, I use this cancellation method. I got this TBA, right? So I know TBA and TBA is inverse of TAB, right? So let's say you have RAB and you know the P. You want to know what TBA is. So you could use the inverse relationship to find that.
Oh,
Now this is from the previous slide that I showed. This is the one you want to put on your cheat sheet. All right. So let's say you know point, there's a point PC, you know PC, all right, this is known. You don't know what PA is. This is unknown. And this is known, TAB. This is also known, TBC. Find what PA is. Find a relationship, write relation. So also just find PA, but it means that because you don't have anything, just write what the relationship is, find PA. So where do we start? Usually that should be a question because you have all the knowledge, you have everything in front of you. What should I start? So we know that we have the location of P in another reference frame, right? So on one side, we know we have PC and we need to find PA, right? We need to find something that can fill that. What can I use in that relationship? You could use PAB to BC, which is basically what? PAC. So you basically needed TAC, right? But you said, I don't have it, but I have the other way around, right? You have this too. So then you can write that here. So then you say, okay, I don't have that, but I know I have TAB and TBC. Right? Now your problem is solved. Like if you have the numerical value, you plug in there and you're good. Again, remember, if PC is given to you as, if let's say PC is PX, PY, PZ, what's that extra mile you need to go? What's the thing you need to do? Add one, right?
Well, we start with PC. Right, so don't we want to go this other way?
Hmm?
We start with PC.
We need to find PA, right? So we need the
And then
location
why
of
are we
P.
getting A to-
You need to find where A is in this frame,
Yeah,
right?
right.
So this is your original frame. So you're using TAC.
Okay. Even though the point that we know is in,
So my pole, I'm always using him.
yeah,
So basically, we know where he is with respect to that coordinate.
Okay.
We want to know where he is from my point of view, right? I need to know this transformation. How is he rotated and moved with respect to me? If I have my position to there, which is from this relationship. I don't have this. I need to find what is this rotation transformation,
okay.
right? If you can, if you didn't understand, there's another example after this that has numbers, so you can see from there.
That makes sense.
All right, so what we have to do, we know TAB, TBC, they are 4 by 4. So this is PX, PY, PZ1. So I might not always give you appended. I'll give you a point because that doesn't make sense in Cartesian. This makes sense in Cartesian. Right? All right, example. So this is basically what we just did. Try to express coordinate P in frame A. You have coordinate P in B. So I'm gonna write what are your knowns. So your known values. You have PB 0, 1, 1. You know P translation. So you should write P trans 0, 3, 1. So this is the translation between the center of the two frames. All right. This one. This is the transformation, translation between the two. You have that point. All right. And your unknown value is PA. You're trying to find that. We should have everything else. It's not for submission, but I'm gonna walk around and see what you've done.
I'm confused. What do you mean by like, meaning in switch frame?
There are two different, listen, there are two different ways, right? When you do translation, you are thinking the center of this, the origin of this, with respect to origin of this. That
You want, instead of being like you have a random reference space one and like random reference space something else, they're in the same space.
this is in Cartesian 3D.
Yeah.
You don't have any random, and you don't have random, right? This is frame that we started from A. Okay? Let's say there was a car here. It's moved to that new position. What does this mean? This translation. What does this translation mean? 0, 3, 1. It moved along x-axis for 0, y-axis for 3 units, z-axis for 1 unit. That's what translation is, along different axes. It's always the, so remember rigid body, you pick a point on an object, and since it is not squishy, it doesn't matter where that point is, it's representing the whole object. So it could be a car, a robot, a ball, whatever. It moved, translated like that.
So what I'm wondering, of course, these reference frames, like they are like it's not a big part of their
You know, final transformation. What is transformation?
well, I mean, I understand transformation, you're looking for the origin, that the origin.
What is transformation? From one frame to another. Everybody can
The
solve.
movement is a movement along the
What is that movement? Okay, transformation is mixed of two. The other thing about on translation from the objects by accessing the original.
I was thinking about
Prior to the location of them, they're all important. Good thinking, that's just the only thing you need to fix. Yes. I'll go there.
Yeah. Oh. Oh, yeah.
All right, what are the things that we also know, but I didn't put it up there for you, because I want you to think about. So based on what we talked over there, we need to know what's PA, right? And we have PD. What do we need between them? So I need TAB, right? What's TAB? Right? You have both of these. P trans is basically the amount this was translated. RAB, you can write it. You have all the axes direction, right? You just have to write where that is. And then once you have it, you multiply and find that. Sound good? So I'll put the solution, it's fine, I'll put the solution on the updated version. So study this before Wednesday. If there's going to be in-class participation, I'll give you extra time. I will grade that. Yes. Okay. I'll go over one more time. If anybody needs to leave, you can, because it's time, all right? So think of, do you want to come here so I can just explain to you? So I'm gonna close Zoom.